let's talk about the difference between a Z transform and the DTFT. Just going to write down what the definition is of X of Z because it's easy to forget. The Z transform is that sum of our time domain waveform times our Z to the negative N. And our DTFT, we said, was the sum of our time domain waveform times E to the minus J omega N. And so if you take a look at this and this, you can see that Z is like E to the J omega of the DTFT. And what that means is that if we evaluate Z, if we've got the Z transform is really complex. Its input Z is complex and its output X of Z is complex. To graph this thing, we'd need four-dimensional space. We need a plane of values for our Z with a real part and an imaginary part at right angles. And then we'd need two extra dimensions to graph its output, its real and imaginary part, or its magnitude and a phase angle. But if we're just looking at our input here at our Z, if we evaluate that Z around E to the J omega, which is around the complex unit circle, you have the DTFT. And so what I mean graphically, here's our real part and here's our imaginary part, and this is our Z plane. So these are the numbers we're going to put into our Z transform. And if you evaluate it, here's our unit circle. And if you evaluate the Z transform right here, that's like evaluating the DTFT right here at omega equals 0. And if you evaluate this Z transform over here at omega equals, let's see, this would be pi over 4 angles, you'll get a complex value. When you plug in that value of Z into your Z transform, into your Z transform here, you'll get a complex number out, which will be your DTFT at omega equals pi over 4. So this is our input, remember. So you're going to get output a complex number, and that complex number, its magnitude would be graphed at this point, and you can continue this all the way around. You can find what it is for this omega equals pi, and this would correspond to that highest possible frequency over here. And now you can see graphically why, as you loop it around, all the way around, that would be omega equals 2 pi, you have to get the same thing as at 0. So you just unwrap. If this is our Z values, you'll plug in all these Z values around here into your X of Z. I can't graph your X of Z on here because it requires an extra 2 dimensions that I don't have. But if you could then unwrap say that, if let's just think about the magnitude of X of Z, that would be then a height over this plane here. And if you were to unwrap that height over here, you'd end up with the DTFT. Questions about that? I want you to firmly have that picture in your mind, that the DTFT is actually a wrapped around version of the, let's just call it height to break down the number of dimensions of the output, of the height of the Z transform evaluated around this unit circle. Any questions on that before I go on?
I was going to ask if you could repeat that last sentence. Something about the height, unwrapping the height.
Let's say that this is a picture of X of Z. And of course, this is just the Z part of it, because Z is complex. Now, I would really like to graph what X of Z is, what the Z transform is, so you could see it. And the problem is that it requires an extra two dimensions. So just to make what I'm about to say more easy to understand, let's say we're only interested in the magnitude of the Z transform. So now I've got this extra, now I've got 3 dimensions, 2 dimensions of our input variable, the real and the imaginary part, and then the single dimension, the magnitude of x of z. So imagine that as a height. And so we've got this surface now that exists, and that surface over this flat plane of the screen, that surface is the magnitude of x of z. So for any value of z, a complex value z that I put in, there's a corresponding height, which is this x of z. Now, if I was to take a cookie cutter and cut out a circle in my height graph, so the height graph looks kind of like a circus tent. And wherever we had a pole in here, wherever we had a pole, that circus tent would be poked all the way up to infinity. And wherever we had a 0, that circus tent would be poked down to the ground. And so you've got this neat 3-dimensional surface. If you were to take a cookie cutter of that, this infinitely thin ribbon cutter, I guess you'd need 2 cookie cutters, one here and one just outside it. So you're left with a circular ribbon. And then you cut that circular ribbon here and unwrapped it between 0, you know, it's how long is it? It's 2 pi long, right? It starts here and it's a circle of radius 1, so it's going to be 2 pi long. And if you were to unwrap that height of it around the circle would be its DTFT, would be this picture. Is that a clearer mental image?
Oh, that's beautiful. Thank you, sir.
Sure. So now you see that the DTFT that you had was really just an insight into what this magnitude of x of z was in 3 dimensions. But it's doing stuff over here. And the z transform, again, is important because for this example here, we said, hey, we can't take the transform of 2 to the n. It blows up. So all that means is that the circus tent over here would be of infinite height out along this unit circle. But if you go out further out from the unit circle, if you go out at least 2 units from the origin, right here, if you go anything greater than 2 units of the origin, it all of a sudden drops from infinitely tall to something that's finite. And now that Z transform does exist, and now you can do neat things with it. Practically, what does that mean when you use it? Almost nothing. Because remember, the only thing you care about is the z's are only important just so you can take the transform of the input and then the transform of your system transfer function, multiply them together to find your output, and then take the inverse transform out. So you don't care about that the z only exists out here for greater than 2 because eventually you're going to inverse z transform and the z goes away. All that you care about is that the z transform exists somewhere so that you can do the z transform trick. Here's a program that I wrote that shows how the Z transform works in the frequency domain. So here's the Z transform in the Z domain. Here is the DTFT of this. This middle part is pi, omega equals pi. This last part is omega equals 2 pi. And remember, what this is in height is our height of this Z transform surface as we trace it around this unit circle. So as we trace it around for omega equals 0, the height of this happens to be, I guess, 1/2. And then as we trace up here, eventually at omega equals pi over 2, we hit a 0. So at pi over 2, it is indeed the output, the DTFT is indeed 0. Then it gets higher as we increase our frequencies, we get closer to our poles. It is. And then we hit a 0 at higher frequencies, and now we're back to our original here. Who's with me? Walt, tell me what would happen to the middle as we move our poles to the left?
Would that make the frequency like the energy density go higher?
Yeah, let's check it out. And you can see it dynamically as we get these poles closer and closer. And if we put them on the unit circle, this thing would go up infinitely high there. And now it's infinitely high. As we brought it back, we might even see it dip down in the middle here. And that frequency here, whatever this is, roughly what, a little bit less than maybe 140 degrees or so, corresponds to where this omega is here. And if we wanted to bring this to still further down, Hayden, what could I add over here to bring this thing down to 0?
Would it be another pole?
Not a pole, because if I put a pole here, the poles, remember, are like a circus tent. They're going to push it up to infinity. So instead of pole, it's going to be a 0. And that'll pull this thing right down to 0. In fact, I can make this go to 0 anywhere I want to just by putting a 0 at that corresponding frequency. So you can see here's anywhere I want to. I can even put it right next to a 0 and have it alternate between something really high and really low. I could put another pole right here, and you see 0, 0, 0, pole 0, 0, 0, pole 0. So you can control your own, you can build your own filters that way.